dessert, the ice cream choices are chocolate, vanilla, and toffee, and the topping choices are chocolate, caramel, and strawberry. How many different desserts can be ordered? Well, we're going to look at the two choices. So you have a choice of ice cream, which are chocolate, vanilla, or toffee, and then you have a choice for the toppings of chocolate, caramel, or strawberry. So on this first type of ice cream, chocolate, I could put a chocolate topping on, I could put a caramel topping on, or I could put a strawberry. So I'm going to put a chocolate, caramel, or strawberry. So there's 3 different toppings I could put on that one. This one, I could put 3 different toppings on. This one, I could put 3 different toppings on. So basically, I'm taking 3 from 3 choices of ice cream times 3 from 3 choices of toppings, and that's going to give me 9 total choices. What I just did there, that is called the fundamental counting principle. So the fundamental counting principle says that if you have a certain amount of choices and then you have another amount of choices, you can multiply those choices together to find the total amount of options that you could have. So we're going to have 3 times 3, which gives us 9 total choices. And you can do this type of thing with like outfits. So maybe in your closet, you got 10 pairs of jeans and you've got 20 pairs of shirts. That means that you could have 200 different outfits from those amount of clothes. Heading down into example 2 here, sample space. So a sample space in probability is the possibility of all outcomes. So it's a set of all possible outcomes. So I'm going to go back to that lottery example. The sample space of the lottery is 292 million. There's 292 million different outcomes that could happen from those 6 numbers in the Powerball jackpot. An event is the outcome or set of outcomes. So the event would be like your Powerball ticket. So that's the outcome that you would want. Or if you bought multiple Powerball tickets, it would be the set of outcomes that you need. The second type of counting principle that we can have is called the addition counting principle. So addition counting principle looks at when you have choices that are one or the other. So you see this word or in these types of situations. So anytime you have a word or, when you're looking at counting up your outcomes, that's going to lead you to use the addition counting principle. So here, we're going to look at example A here. We're going to look at in a local restaurant, you have the choice of 3 beef dishes, 4 chicken dishes, or 2 vegetarian dishes. And here's that word or right here, which I changed the letters around. Or is going to mean that we're going to add up the total amount of outcomes that we could order. So if we have 3, 4, and 2, I would add those up. 3 plus 4 plus 2, and I'm going to get a total of 9 possible outcomes that I could order food from. So I've got a choice. I cannot order one of each. I've got to get a total of just 1. So I'm going to have 9 total outcomes. Part B, we're going to choose a prime number or a multiple of 4 or a multiple of 9 by choosing a random number from the whole numbers 1 to 20. So here we got to count up all the prime numbers from 1 to 20. So we'll just count up. 2 is the first one, 2, 3, 5, 7, 11, 13, 17, and 19. So there's a total of 8 prime numbers from 1 to 20. Multiples of 4 would be 4, 8, 12, 16, and 20, which is a total of 5. And then multiples of 9, there's a total of a 9 and an 18, so there's only 2. So what are the outcomes if I could choose a prime, a multiple of 4, a multiple of 9? I could have 15 different outcomes. Now, those outcomes that I was just adding up there, those are called mutually exclusive outcomes because each outcome, each category, prime number, multiple of 4, multiple of 9, they each have their own set of outcomes and they don't share any outcomes. So if you have a prime number, it's not going to be a multiple of 4 or multiple of 9. If you have a multiple of 4, it cannot also be a multiple of 9. So that is called mutually exclusive. That topic, mutually exclusive, is something that we continue to practice with. So right now it's just like all right, here's kind of an introduction to it, but we'll continue to investigate mutually exclusive. So heading down to work with the fundamental counting principle some more. So again, fundamental counting principle deals with multiplying, and the addition counting principle deals with adding your outcomes. And that's where you're looking for that word or. When you see that word or, that would represent our addition counting principle. So here, multiplying our outcomes. So here we've got a student is choosing a 4-letter password for email. How many passwords are possible if letters are repeated? I'm just going to use like a little hangman diagram here. So here's our 4 possible letters for our password. Since there's 26 letters in the alphabet, I got 26 options for that first letter, anything from A to Z. Then, since letters can be repeated, I've got another 26 options for my next letter, then another 26, and then another 26. I've got 26 times 26 4 times, or I could do 26 to the 4th power. And for my number of passwords, that's going to give me 456,976. So only 400,000 passwords. It may seem like a lot, but for a computer just to maybe hack into a password and check all those passwords, it'd probably be pretty quick for a computer to do that and check all those and see which one's going to work if they're trying to hack into your computer. That's why most websites are going to represent 8 letters, and then you could use numbers, letters, and symbols. So then you get up into the millions and even billions of different passwords, which makes it a little bit harder to hack into. Most hackers now, they'll use your security questions, so they can get onto any of your social media profiles and maybe find more about you, and then start to guess your security questions. That's kind of how hackers can get into your accounts. Next, how many passwords are possible if letters cannot be repeated? So letters cannot be repeated. Now, once I've chosen 26 letters, I now have only 25 the next time because I've already used the letters. I can't repeat the letter. And then after the next time, I can only use 24 letters because I've already used 2 now. And then at the last time, I could only use 23. So we'll take 26 times 25 times 24 times 23. And this leaves us with 358,800 total passwords. So we could see our passwords dramatically decrease when I throw out all those passwords that have letters repeated. I've now only got 358,800. So that's going to start to look at our next topic where our sample space, as we go from one counting principle to the next, our sample space is kind of changing a little bit. So first I have 26 total letters, and then I go all the way down. So let's head down to our next topic. Last thing we're going to talk about with probability, we'll do example 5 quick. That one won't take long. Independent is 2 probability events where the second event is not affected by the first event. And what we need to understand here is that your sample space is unchanged. So if you want to write that down. And a dependent probability is where 2 probabilities events where the second event is affected by the first event. That's where your sample space changes. So certain types of situations, like if you had a jar of candy at home, like we have a jar of candy from our Halloween yet from our kids. If you have a jar of candy and you want to find out what's the probability of selecting a Reese's out of there. So when you select a piece of candy out, you pull it out, you eat it. Well, when you've taken a piece of candy out and now you've eaten that candy, you've now changed the total amount of candy in there. So the next time somebody goes to reach in and figure out the probability of pulling out a Reese's, you've now got a different probability. So that would be a dependent event. So as you change the sample space, so you got this jar of candy, maybe 100 pieces, you pull one out, now the next person that goes to pick a piece out only has 99 pieces. And then the next person only has 98 pieces. So when that sample space changes, that's going to be a dependent event. Looking at example 4, we've got 5 coins that are in a bag. What's the probability of choosing a penny and then choosing a nickel if the penny is not replaced? So that's going to change it from 5 total coins to 4 total coins. That's going to be a dependent event. So when you pull out that penny and then do not replace it, it's now changed the total amount of coins to only 4 coins in there. Part B, you choose a penny, then a nickel, the penny is replaced. Well, now when you replace that penny back in there, now there's 5 coins again for the next time somebody goes in to choose a coin. That's going to be an independent event. So the dependent, your sample space changes. Independent, it does not change. And lastly, we have 8 students that are working on a school newspaper. If the 8 students will be lined up in a row for a picture, how many ways can the students be arranged? Well, in our first position, let's just say we're going left to right. I have 8 students that could be in that spot. Once I set somebody in that spot, now I've only got 7 to choose from for the next spot. 6 all the way down to the very last person. And I can multiply all those out. And I get 40,320 ways that they can be arranged. And this is a very common pattern in probability when you multiply consecutive numbers going all the way down to 1. And that's called a factorial. So really that would be 8 factorial. And the factorial is actually an exclamation point. So exclamation point is a symbol that is used in math and mostly statistics. And that would be our 8 factorial. So just starting to introduce some of our counting principles. So we have a few problems to practice on Delta Math, and most of those are word problems. So you can always send me screenshots if you need help if you're working on it. I'll be on until 8:10. Sorry, it is 7:59. We went a couple minutes over today, but we are free to break off if you're ready to work on your own, to work on your counting principles. But I will stay on the line till 8:10 to help out. Again, thanks for waking up and joining, and we will see you possibly tomorrow if you need some help, or we'll see you again on Monday. So have a great weekend if I don't see you, and you are free to break off on your own to work, and I will be here to help with any problems that you need. Thanks, Morgan. You too.